Okay, hi, I'm Holly. I'm a second year PhD student, and my line of study is to look at molecular abundances in end-of-life stars such as supernovae. So for this talk, what I'll be focusing on is mostly the molecule or molecular ion HCO plus in one specific supernova, which you can see in this lovely photo here. It's supernova 1987A. So let's get started. So the aims of this project are to investigate the distribution of HCO plus within the ejecta of supernova 1987A, and to compare this HCO plus distribution spatially with those of carbon monoxide and silicon monoxide also found in the ejecta. And then hopefully using the line intensities or the fluxes of HCO plus, we can find an estimated mass for this molecule within the ejecta of the supernova. So first things first, just a little bit of background on this specific supernova. So it exploded on the 23rd of February in 1987. And what's special about this supernova is that it was quite close. So the Large Magellanic Cloud, and it was very bright. So we could get a lot of information from it in the 35 years it's sort of been around. It has exhibited emission in all regions of the electromagnetic spectrum and has exhibited a whole host of molecules to be detected, such as carbon monoxide, silicon monoxide, sulfur monoxide, and also hydrogen gas. And it's comprised of these sort of three regions. So you've got like this sort of red outer rings here. You've got an inner orangey equatorial ring, and also this white blob in the center here is the ejecta, which we'll be mainly focusing on for this talk. So it continues to surprise us even today with the amount of things that we can detect and discover within it. And one such surprise is the detection of HCO plus within the spectra. So it was first detected in 2017 by Matsuura et al. In significant quantities as well. So I can just point out the two transitions that we found in Segan et al.'s paper in 2019. So there's the J equals 3 to 2 transition here at 267 gigahertz. And then you have a higher transition of 4 to 3, which is here at about 257 gigahertz. Now, why is this molecule such a surprise to detect in this young supernova remnant? Well, HCO plus, as you well know, is common in molecular clouds. And in fact, this equation down the bottom here shows the primary reaction route within a molecular cloud or a typical molecular cloud. So it requires both H3 plus carbon monoxide in order to form it. And however, the time scale of this formation is fairly long, and it doesn't make sense for a 35-year-old remnant to have HCO plus in such quantities, even though it's quite a young supernova remnant. And actually in literature, very few supernova chemical models actually predict the outcome or the yield of HCO plus within supernova remnants. For example, I found one piece of literature from Rawlings and Williams back in 1990, and it predicted a mass of about times 10 to the minus 18 solar masses for HCO plus, whereas Matsuura et al. Found the mass to be roughly times 10 to the minus 6 solar masses. So a significant difference between the two, the predicted and the observed models here. So what we're thinking is that there might be an additional driving factor present within the remnant, which might be hydrodynamical in nature, to explain why such quantities of HCO plus forms. So this additional driving factor could be macroscopic mixing. And in order to understand macroscopic mixing, we need to go back to the elemental burning zones of a high mass star before it explodes, which can be seen in figure A here. You sort of have these stratified elemental burning zones, a bit like layers of an onion. And at the core, you have the heavier elements being synthesized. So for example, silicon and iron. Then at the outer layers, you have the lighter elements such as helium and hydrogen. So these elements need to mix somehow in order to form HCO plus, because we need the hydrogen to mix with the oxygen and the carbon. So During the explosion, these shells are blasted outwards. And because these shells have different densities, it gives rise to certain instabilities. One such instability is known as the Rayleigh-Taylor instability. And what it does is there's a lovely diagram appeared by Hammer et al. In 2010, which shows the sort of geometry of an instability in this supernova remnant. And what it does is like these massive clumps of material are sort of outwardly mixed, but also materials inwardly mixed. And another visualization of this would be pouring milk in tea or coffee, for example. So yeah, how do we detect HCO plus? So we would need the spatial distributions of HCO plus in order to find whether this macroscopic mixing does occur. And for that, we need a very powerful and sensitive telescope with high angular resolution. So of course we used ALMA. And these are just the basic parameters which we got from finding the two transitions. So J equals 3 to 2, we use band 6, and the maximum baseline is about 8.5 kilometers. And for 4 to 3, we use band 7, and the maximum baseline is about 1.7 kilometers. And for both transitions, we use the 12-meter array configurations. So what does this data look like? Because the remnant is still expanding, the emission is actually broadened at about 2,000 kilometers per second either side of the rest frequency of this transition. And so what we can do is we can split up this velocity or this frequency into different chunks, which is seen here in this data cube. So the 0 kilometers per second corresponds to the emission at the rest frequency, and so on and so forth. And you can see just by looking at it that most of the emission is contained within the central few slides. And also it's quite blobby and quite clumpy, right? Which is a good indicator that it supports macroscopic mixing because the structure itself is quite clumpy. And in fact, the formation of HCO plus within this ejector itself, the actual existence of it, implies that a significant amount of both carbon monoxide and hydrogen have been inwardly mixed to form this stuff. So this is really good news. However, what we can do to further support our conclusion is to compare it against distributions of carbon monoxide and silicon monoxide. And we found data cubes from Abelin et al. In 2011 and Segan et al. In 2019 to compare these with. And on the right here, you see a data cube corresponding to the 2-to-1 transition of carbon monoxide. And you can see it's fairly blurry, right? That's because the resolution was matched to match that of the HCO plus resolution. But you can see as well that this form is quite clumpy as well. You have like these bright regions and regions of lower intensity in these sort of blobby regions. And the reason why SIO is also involved in analysis is just as a control. We expect there to be similarities between carbon monoxide and HCO plus distributions because we think that they're linked somehow from the primary equation that we saw in the first few slides. However, we expect very few similarities between SIO and HCO, which we have found. So that's good, in other words. So again, just to show the distribution of SIO compared to CO, again, it's the clumpy structure, blobby structure as well. So that's good. So what I did next, just to further confirm that HCO plus and carbon monoxide are sort of linked in a way, I took a contour of the CO emission and I overplotted it on the HCO plus emission. And as you can see, the overall shapes of the emission are the same or very similar. And the fact that the bright spots of HCO plus coincide with some of the bright spots of carbon monoxide as well, which is very good to see. So it indicates that carbon monoxide does form HCO plus within this, or there's a high possibility that carbon monoxide does form HCO plus within the ejector. So yes, I talked about the lower line transition of 3 to 2. We had no such luck with the higher line transition of 4 to 3. As you can see from this CASA viewer image here, it is not spatially resolved. And you can tell by the high angular beam size as well. So again, we can't do the same sort of spatial analysis for the higher transition. However, what we can do is that we can extract the flux or the line intensity from it. And when you have two line intensities, you can find the mass of the molecule, which I will do further down the line using the radiative transfer code RADEX. And again, the line intensities here are preliminary, but we find them to be in the range of × 10 to the -20 watts per meter squared. And in literature, Matsura et al. Had already estimated the line intensity, but because we have used interactive cleaning and interactive aperture photometry, then there is a discrepancy between my values and their values as well, just because of how interactive it is, and it's quite difficult to reproduce the results. So just to recap current findings, ALMA observations of the J = 3 to 2 transition line are spatially resolved, and that the clumpiness of this transition line supports the theory that the supernova remnant has undergone some macroscopic mixing, and that the spatial distributions of HCO plus at this transition with CO are visually similar, which supports the theory that HCO requires carbon monoxide to form. So thank you very much for listening to my talk, and it's a great pleasure to be here. Any questions?
Thank you so much, Holly, for the excellent talk. This is a really interesting topic that is not usually discussed with ALMA-related studies, so it's really great to have your talk here discussing supernova remnants.
Thank you.
Do we have any immediate questions?
There's nothing in the chat, so maybe I can ask. Are you planning any follow-up observations of HCO plus maybe with band 5? Then you would get, I think, the 2 to 1 it is?
Not at the moment, but that is a very good idea to have, actually. Just
maybe you will, this might be stronger and more resolved.
Yeah, possibly, yeah.
Yeah. Okay.
Yeah, I'll pursue that. Thank you.
Is the ALMA proposal deadline coming up? Just saying.
Oh, okay, yes, I'll get writing right away.
Always good to get band 5 projects. Okay, so there's another question. From the 2 HCO plus lines, can you determine some estimate of the temperature of the gas? Do you expect it to be too high?
Yes, that is an additional thing that can be uncovered using RADEX in particular as well. At the moment, I still have yet to do that, so I'm not entirely sure on the temperature at the moment. Yes. Apologies. Check back in a few months.
We're looking forward to those results. There's another question. Could harsh environment in the ejector, cosmic rays, hot electrons, so on, make the analysis and the mass estimation more difficult?
Yes, that is a very good question, especially at the moment in sort of present day. What's happening is that the reverse shock wave is actually reaching the ejector now. And it's entering like a new phase within the remnant itself. So a lot of those molecules which we have detected are going to be destroyed by X-rays. So yes, the current understanding is that if you get a sort of idea of how the abundances of molecules and stuff originate now, and then in a few years' time after the shock wave has passed, or a few decades' time actually, after the ejector has surpassed the shock wave, it might be good to compare these abundances later on, just to see whether the supernova can recreate these molecules after this destructive shock has sort of destroyed them, if they can reform or not.
And that's very exciting that you can see these kind of changes in our lifetimes. It's not so typical for astronomy studies, right?
Yeah.
Really nice. There is another question, what the physical interpretation of HCO plus is.
Yes, so from previous brilliant talks, we've seen that the HCO plus can be used as a tracer for dense gas. However, in our case, what we think is that it could be a tracer for the amount of mixing within the remnant. So at the start, when I was talking about the hydrogen mixing with the carbon and oxygen, so just seeing this molecule here indicates a lot of mixing has been done within the remnant.
Can I ask a question?
Of course.
Yeah, so this might not be directly related to your work, but can you tell me about how long is the molecule supposed to survive once it's ejected out, and whether we can say something about the enrichment of the molecule in the interstellar medium, whether what we see in especially dense environments, whether it's primarily coming from these supernova remnants or from some other origins?
Yes, that is a really good question, and I'm not entirely sure on the answers to it at the moment, I'm afraid.
No worries, yeah.
Yeah, I'll get back to you.
Do we have any final questions?
I only see a comment from Sebastian, who says that we do see molecules in Cas A, so molecules should indeed survive or reform after the reverse shock. But of course, it will be indeed interesting to study this in the supernova remnant as well.
That's good to know.
Excellent. If we don't have any more questions, thank you, Holly, again for the excellent talk and answers.